Right, turn the volume up. Here we are again. This question is about change in state. Change in state. Change of state. Okay. This one we go in. So it's going to be solid, liquid, and gas. Okay. So we've done a bit in class before, but this one is we've got to work out. So first of all, we've got 50 kilograms of ice or water, because water at minus 27 is ice, right? But we've got 50 kilograms of ice at minus 27, so it's solid. It's heated to turn it into steam at 100. So we want to heat it, melt it, and evaporate it and turn it into steam. Stick in a turbine or something. So we need to work out the heat, the energy we need to get this minus 27 block of ice up to steam, fully steam at 100. How much energy we need, right? So these calculations, we're going to use these constants. Heat capacity of ice, heat capacity of water, right? The latent heat of fusion of water and the latent heat of evaporation of water. I would do this if I was you. I would get a little diagram just to show our phase diagram. And it's going to do something like this. So we've got, what was it, minus 27. So we've got minus 27 here. This is our energy, as I call it U perhaps, and this is temperature. So we've got 50 kilograms of ice, and we're going to warm it up. The more energy we add, up comes the temperature. Bang. Comes to a point. Right, this down here now is solid. Solid as ice there, isn't it? Right. Gets to a point where it starts to melt. That normally on Earth at ground level is 0. Melting point. And then we get this little latent heat of fusion. Right. If you remember, what's happening there is we're adding energy, but the temperature is not being changed or go up because we're using the energy to break the bonds. We're breaking it from a solid to a liquid. So it gets to the end of that when it's all liquid, and then it starts to go again. So this is liquid. In our case, water, isn't it? Because we've got ice, we've got water. So this is the liquid phase. We've gone from the solid ice phase to the liquid water phase. And then it'll start to change phase, let's say, when it goes to a gas, water at 100, known as the boiling point. This could be the melting point. Starts to evaporate. Okay, so this is the latent heat of evaporation. It's breaking the bonds, turning it from water into a gas, into vapor, to steam. Okay, and then it's into steam. That's where the gas bit is there. Look, gas, steam. I suppose vapor because we're water, but it's the gaseous stage. So we've gone from minus 27 all the way up to 100. It's evaporated, turned into a gas, gone into a cylinder, steam engine, something like that. We've got to find the energy to do that. So we want to go all the way up. From there, all the way up to turn it, right, to start melting it, all the way across the flat, all the way up to turn it into 100 degrees water, and then all the way there to turn it into gas. The formulas we can use is this: change in energy. If you remember, M times M is the mass, C is the, if you go up, look, the specific heat capacity, and then we have difference in temperature. Okay, And then when we're going along the flat bit, this bit here, we've got this now is called fusion. Latent heat of fusion. The bonds are breaking. Okay, and this is evap. Okay, I've labeled them both like that. Some people tell me off, but it's my video. So latent heat of fusion of water is 334 kilo, and the latent heat of evaporation of water is 2.26 mega. It takes quite a lot to turn it into gas. So when we come to them bits, we're going to be using the mass times by this UI thing. So that's the only two formulae we need. So I've got my first stage, stage 1 is here, look. We're going from minus 27 to 0. So starts off 1. So the energy I need to go from minus 27 to 0 up this first slope is going to be M times C. Now it's ice at the start, so we need to find the heat capacity of ice. So sea ice, not sea ice, not ice from the sea, but sea ice is 2.14 kilo. So I'm going to put CI there, look, sea ice times by change in temperature, which is going to be 27, because this difference is 27. So I'm going to put in here now, what's the mass of gas? Sorry, the mass of ice is 50. So I'm going to put 50 by there, times by the heat capacity of ice, because that's the stage we're at. Ice is 2.14 times 10 to the 3 is kilo, look, there's the kilo. So I'm going to do this, 2.14 times 10 to the 3. That's the capacity of ice, 2.14 times 10 to the 3. And then the difference in temperature, that triangle T means delta T, means the difference in temperature, which is going to be 0, take away 27, and 0 minus 27. So the difference in temperature is 27. So times that by 27. This will give us the energy to go from minus 27 to start to melt it into water, look, all the way up that little hill. If you put that in your calculator, you'll get a number like something like this, 2889 joules. That's how much energy we need to do that. Lovely. So now we're at the. So now we're here. So now stage 2 is to, right, it's starting to melt now. So we want to turn this ice into fully melted water, which means we've got to go along this flat bit. This is the fusion bit where we're breaking the bonds apart. Not fission. Fission is a different thing. Fission is colliding them like the sun does. This one, we're breaking the bonds to turn it into water. So the formula for that is this thing by there. Okay. So stage 2, energy is going to be M, which we know is 50, times by this thing called UI, which is the latent heat of fusion of water. By there, look, 334 kilojoules, latent heat of fusion of water. We're turning the ice into water, so it's going to be 334 kilo. So the mass is still 50, because we're not losing any mass, times by that value, which was 334 kilo, which is 10 to the 3. That'll give you how much energy to fully melt it along that stage. That should give you something like this, 167, 1, 2, 3. That's how many joules we need. So what we've done now is we've taken out minus 27 block of ice, and we've gone all the way up, all the way across. So now it's fully melted. It's water at 0 degrees, so there's no ice left. It's not like a slush puppy, it's just water. So now we're going to go up this hill. So we need to work out now how much energy we need to turn this water to start to evaporate it, to change stage, change phase. So number 3, because that comes after 2 normally. So number 3 is going to be energy, look, change in energy. It's going to be M times C again, times by change in temperature. But this time, we're now liquid, it's water now, so we've got to use the specific heat capacity of water. So now it's water, which is 4.2 kilo. Not ice anymore, it's turned to water, so it's a different property, different material in theory. So 4.2 kilo, that's my C value of water. So, getting bored of that colour. So the mass is still 50. That latent, what was it again? I don't know. Capacity of water was 4.2 kilo. So I put a bracket like that, 4.2 times 10 to the 3 times by the change in temperature. The difference in temperature is 100 naught. So the difference in temperature is 100. Put that in your calculator and you will get a number. And it's going to be something like 21, 1, 2, 3, 4, 5, 6 joules. Okay, so that's stage 3. And all we've done now is we've turned this block of ice. Right, it's come now to this point here, right, where it's starting to evaporate, stuck in a kettle. When you get to about 100 degrees, it'll start to evaporate. Not all in one go, but it'll start to. So we now need to go along this little slope here now. Notice this flat, because it's starting to evaporate. We want to turn it all into steam. So we need to go to this point at the end. Okay. That's going to be called the latent heat of evaporation. 2.26 mega, which is quite a lot. There's a formula. M times this UI thing. So stage 4, to turn it all into a gas, to move a cylinder or something, we're going to go number 4 down here. Change in energy is going to be M times UI. The mass don't change, are still 50. The latent heat of evaporization, can't say it, is 2.26 mega, because we're going to go all the way along that bit there. Turn it into steam, fully steam, no water left, it's all evaporated. Okay. If you ever leave a kettle on and the switch don't work properly, it'll off goes the water and you'll have no water left. So 2.26 mega. So I've got to time this now by 2.26 mega. Move that over the other way. 2.26 mega, 10 to the 6. Put that in your calculator, you're going to get a big number now. You're going to get something like 113,000,000 joules. That's how much energy we need to fully evaporate or turn this water into steam. So now we're right there. So our block of ice is turned into steam. So we've got 4 stages, 1, 2, 3, 4. That's why you should draw a graph or a phase diagram like that, so you don't skip any bits. And now the total, because that's the question, isn't it? I write in red. The total energy needed, total energy needed in joules is going to be 1 plus 2 plus 3 plus 4. don't do 1 plus 2 plus 3 plus 4. I mean that plus that plus that plus, you got it, that. Okay. If you add all them together, you're going to get a big number. You might get something like this: 1535890 joules. If you move the decimal place, 1, 2, 3, 4, 5, 6. I'll put that out just in case I confuse people there. Look. Oh, come on, what are we doing? 1, 5, 3, 5. There's the decimal place. So if you want to press E and G, 153.58 or 9 times 10 to the 6 joules, or 153.5. Okay, you could make that 9, can you? But okay, mega. 10 to the 6 there, look. 10 to the 6. 1.53 megajoules. Okay, that's how much energy we need to turn this steam, that's how much energy we need to turn 50 kilograms of ice at minus 27 degrees into steam at 100. Stage 1, stage 2, stage 3, stage 4. That's why you need a lot of energy to make electricity or stuff like that, because you've got to boil water, or you've got to, get the cold to make the heat. Okay, that's the answer. That's how much energy we need. Done. Right, Benny, North Star.